So welcome. So this is the second part, and what we're going to do is we're going to talk about things on slopes, and before we can do that we need to talk about friction. So here's a situation where we have a block and it's on a slope, on an incline we'd say, and we know that for the downwards force there's a balancing upwards force because it's not accelerating anyway, it's stationary. So, and we can break up this upwards force into a normal component and a frictional component, and the frictional component is the component of this upwards force that's along the surface of the material, and the normal is the component of the upwards force that's perpendicular. But there are two components. Normal does not mean usual, it means 90 degrees too. That's the mathematical expression of the term. Okay, so a 2 kilogram block is stationary. That's a 30-degree slope. So again, we do 30 degrees. A little square, big arrows. That's 2 kilograms, so that's 20. I have a F normal. Frankly, the frictional force will be either up the slope or down the slope, depending upon the circumstances. What can you tell me about the frictional force in this example? Is it going to be up the slope or down the slope? And do you have logic for why it's what you pick? Should I draw it to the up the slope or should I draw it down the slope? For frictional force, yeah. It will be up the slope. And do you have a rationale for why it's up the slope? It's opposing the tendency to motion. And the tendency to motion is down the slope, so if it's stopping that, it must be pointing up the slope. If I was to enter this diagram and start pushing the block up the slope, then the frictional force would first of all be reduced and then maybe disappear and then fight me, you know. But it depends on the circumstances. All you know is it's in the plane of the slope until you go to that next level. Okay? I want to find the normal force. So basically, let's change color ink so that I can see what I'm doing here. I don't want the frictional force. So draw a line that's perpendicular to the frictional force. And then it's called resolving your forces. Resolve your forces along that line. Well, that 20 Newton as a component, and so does that frictional force. That normal force is its own component, and that does not. If this is 30 degrees here, then that's 30 degrees there. Can you see how easy that is to see when you don't use 45 degrees as your angles? It's the small angle. It's not the big angle, it's a small angle. So it's got to be 30 degrees. I can look at this and I can say this is going to be 20 cosine 30. I can look at this and say this is going to be Fn. I can say this is going to be positive Fn. I can say this is going to be minus 20 because I want my minus down here and my positive. I say the sum of the forces along the purple line equals 0 plus Fn added to minus 20 cosine 30 equals 0. Fn is equal to 20 cosine 30. Fn is equal to, I actually got my calculator while we're on break. 20 cosine 30, hold on, Got to put my glasses on to see what am I in. I'm in degrees, yeah. 17.32. Done. It's just by being clever about where I put the axis, it just makes life so much simpler. And it's not that hard. You know, if I was to do horizontal and vertical, I'd have a bunch of components. I have to work out a bunch of angles. I'd still have to do geometry because I'm not giving you the angles. You still have to do some geometry. So, sorry, I'm just. Is that okay? Can I? Anybody still writing? Okay, cool. Let's talk through this one. So block is stationary on an inclined rough surface. So it's a 30-degree surface. So boom, 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 boom. Then you get your protractor and you draw 30 degrees. Then you put a little square on it. And then you get your protractor and you draw downwards. And that's 2 kilograms, so that's going to be 20. And then we draw a nice FN, and we draw a nice FF. And then I get my thinking cap on, and I say, I don't want to find the normal force. So I'm going to pick a plane that's perpendicular to the normal force. And then I say, okay, resolve your forces along that line. Well, that one's not got a force component along that line, but that one is in the line, so it is, if you like, its own component. This guy, if this is 30, then that's 60. And if that's 60, well, you can turn around and say, let's just say that. This would be 20 cosine 60. I was going to work out the angle down here and say that it would be 20 sine 30, which is the same as 20 cosine 60. I've learned over the period of time that whatever angle I have in that corner is the same angle I have down here. So it's just the sine of it, but that's just familiarity. Let's call that positive. Let's call that negative. That means that's a negative. The sum of the forces along the purple line equals 0 plus FF added to minus 20 cosine 60 is equal to 0. Apply the law. FF is equal to 20 cosine 60. 20 cosine 60. 10. Print a box. Can you see how that diagram is either going to help you or it's going to hurt you? And, you know, we're training for statics, and statics is a lot more involved than this. So the idea that you can just kind of like shove numbers into an equation is not going to make it. So if you're looking at that diagram and going, I could never do that, then you need to, you know, ask for help. You can do that. It's just practice. But it's really all about visualization. At this stage, it's all about visualization. a lot of people do good math on the wrong problem. You get nothing for it. So if your problem is components, because you don't know your sine, your tan, and your cosine, then learn them. That's bookwork. If your problem is components because you keep drawing the wrong diagram, which it was for me, then you've got to resolve that. And that's not a math problem. That's a visualization problem. That's a physics problem, really. And it's not like you're the only person who ever had trouble with that. It's like we all have some trouble with it. It's just we get through it quickly or we get through it slowly. But without a decent diagram, whatever you do is harder. The diagram is not a challenge, it's an aid. And I know at the beginning it seemed like a challenge and not an aid, but it's an aid. It makes you more powerful. It makes what you need to do easier. It's just like you've got no serve, you've got to develop a serve. You're not going to get anywhere without a serve, so you need to practice it. And it's the same with that. If you don't do diagrams, you need to do diagrams. So there it is. By the way, if I'd said a 2 kilogram block is coasting down an inclined plane at 1,000 miles an hour, it would be the same problem. Because it's not about motion, it's about acceleration. Okay? So just bear that in mind. Friction is not just a component, though. It is a thing in its own right, and so we can study it. And so people started putting surfaces. I put a block on top of another table and I started sliding it. And I measure the frictional forces. And in the United States, there's an organization called the National Institutes of Science and Technology. And it's one of those kind of like government jobs that are careers. You know, you're there. Most people who go there stay there their entire careers. And you're paid to do some pure science, which is kind of nice. And people there measure the speed of light to ever more decimal places and the like. And in Britain, there's the similar organisation is called the National Lab at Teddington Lock, and it does pretty much the same thing. And they never run out of things to measure. In the end, you know, when you go to a grocery store and you say you want half a pound of cheese, how do you know that that scale is truly measuring that weight? You take it on trust. But it is supposed to be calibrated. And it's not just they buy the scale and then that's it. Because you know what's going to happen? They're going to find the calibration control and they're going to shift it and, you know. There's inspectors that come round and they have their little bag and they take out their weight and is it reading right? And if it's not, then they make them adjust it. And if it keeps not being right, then they start writing them up for it. So they do that kind of thing. The other thing they do, they don't do that. They make the standards that then the inspectors use. You know. Then the other thing they do is, I invent a new material, Bonaquistium. It's like amazing. And I don't have time to measure all its physical properties. All I know is it's really non-sticky. It's great. So I'm not going to waste my time measuring all this other stuff. Let somebody else work out its density. Let somebody else work out how it reacts with ozone. That's not my job. I'm making it. But you'll find that somewhere like the National Institute of Standards and Technology will call me and say, we'd like some samples. And basically, you know, I'll provide them with samples and then they'll do a whole bunch of measurements on it. And then that information will find its way into the engineer's handbook. And so if you look in the engineer's handbook, it has just a whole section on friction. And it's copper on aluminum, and it's brass of one type or other on aluminum, and it's zinc on copper, and it's one type of stainless steel on another type of stainless steel, and it's birch on elm, and it's PTFA on brass, and they're looking at all these combinations because friction has to do with both surfaces, not just one, it's both surfaces. And they work out figures of merit. And the figure of merit that they use is the coefficient of friction. It's this fractional number. It's not got any units, it's just a number. It's the ratio of the frictional force to the normal force, as it turns out. Why the normal force? Why not the weight? If I have the block, I can see how friction arises. There's the underside of the block, and there's my smooth table. And what's happening is the two are becoming enmeshed. And so when I try to push it to the side, it's like it's not easy. Even when they're not enmeshed, even when they're just already sliding, there's some enmeshment that takes place. It turns out the more I enmesh them, the bigger the frictional force is. And it turns out that although when you're on a horizontal surface, the weight is what enmeshes them, what about when you're on a sloping surface? Now the weight is tending to cause the motion. The force that represents the amount of enmeshment is the normal force because it's perpendicular to the surface. So we don't use the weight because that only works horizontally. We use the normal force because that works at whatever angle I'm dealing at. And we find that if we do the experiment, if we plot the frictional force versus the applied force. So here's my applied force, and there's the frictional force. What I find is that before I start moving, if I apply 1 Newton, my frictional force matches it, so I don't start moving. If I apply 2 newtons, my frictional force matches it. If I apply 3 newtons, my frictional force matches it. If I apply 4 newtons, my frictional force matches it. If I apply 4 and a bit, suddenly I start moving. And the weird thing is, my frictional force once I'm moving is not as big as my frictional force on the point of slipping. That's very significant. From my perspective, what I'm saying is, when I stop moving, I settle in. And so to get me moving, you've got to work harder than if you want to keep me moving. It kind of figuratively makes sense. A material scientist would say, when you stop moving, you make cold welds. And that when you're moving, you don't make cold welds. So there's this different mechanism taking place. Either way, it's a demonstrable fact that the coefficient, that the maximum frictional force is when you are on the edge of slipping. And that, for instance, actually is why when you're driving a car and you brake, you never want to lock the wheels. If you're driving along and you see all those tire tracks on the road where the people have just left the rubber on the road, that's really bad because they've locked the wheels and they're not getting the maximum amount of frictional force. They're over here. They're sliding the tires across the road. And if they just backed off the brakes and held the car on the point of slipping, so the wheels are still moving, but they're still rolling, they're not sliding, they would get a bigger stopping power. So in my day, when I was learning to drive, there were no such thing as ABS brakes. So you were taught to pulse your brakes. Just pulse, and when you felt it, back off and pulse, but never lock your wheels. But push as hard as you can without locking your wheels. And now we have ABS brakes, and ABS brakes, they do that. Have you ever braked and you feel that pulsing? There's like a pulsing in your wheels. That's the ABS brakes kicking on and kicking off. trying to stop you as efficiently as possible. But without, as soon as they detect rotation, as soon as they detect motion without rotation of the wheels, they back off. And that's what that pulsing is. That's all because of this observation that the maximum frictional force is when you're on the point of slipping, not when you're slipping. So we've got to define two coefficients of friction. There's the static case where the frictional force is less than or equal to a constant times the enmeshment force, which is the normal force. And then we have the kinetic friction. This is motion where the frictional force is simply equal to the coefficient of kinetic friction times the normal force. And what you find is typically the coefficient of static friction is a bigger number than the coefficient of kinetic friction. And these numbers range from 0 up to about maybe 1.5. If you think about it, if you've got an interface which is 1.5 coefficient of, say, kinetic friction, it's taking more force to move it sideways than it would be to pick it up and carry it. So that's a really tacky surface. It's not to do with smoothness. We say smooth table and rough table, but it's not to do with smoothness. If I take two glass slides, which are really smooth, it's very hard to slide one against the other. If I have cobblestones and a wooden pallet, which is really rough, it's easy to push. So it's not to do with roughness, although we talk about smooth surfaces versus rough surfaces. That's colloquial speech. Yes.
Yeah. So for kinetic friction, is that different between an object sliding and an object with wheels?
No. So I'm glad you asked that question. The kinetic friction is when the object is sliding. If the object is rolling, so that the tyre simply touches and lifts off, so normal motion, that's static friction for the tyre. Because although the object is moving, the tyre has just been placed and lifted up. It's kinetic friction for the tyre when it physically slides over the surface. When that molecule of rubber on the bottom of the tyre is dragged across the surface, that's kinetic friction. When it's simply put down and lifted up, that's static friction. Okay, good question. Yep.
Just a question. So, if the block is on a
Incline.
angle and it's staying there, that's considered static, right?
If it's stationary, it's static.
If it's stationary, and then it'll have a frictional force. Now, if the block is sliding, then that would be considered kinetic.
If it's moving, it's kinetic. So this is not like equilibrium. With equilibrium, it's acceleration or not. With this, it's motion or not. So it's kind of different. Yeah. 2 kilogram block sits on a level table. There's 0.4 kinetic friction, static friction between the block and the table. What's the maximum force of friction that can be produced by this system? So let's take an applied force, and that gives rise to a frictional force. And I want the maximum. So this is point of slipping. I say FF is less than or equal to mu static times Fn. Man, I'm going to just move that down a bit because I need to be able to write that. I'm going to say FF is less than or equal to mu s times Fn. On the point of slipping, FF is equal to mu s times Fn. FF is equal to 0.4 times Fn. Oh. I'm being a bit pedantic here. Find Fn using the sum of the forces vertically equals 0. Fg, Fn, Fn plus minus Fg equals 0, Fn equals Fg, Fn is equal to 2 times 10, which equals mg. Yeah? 2 times 10, Fn is equal to 20. Ff is equal to 0.4 times 20, which equals 8 newtons. Now I'm being pedantic there. I'm showing you every last step. Because it's not always as simple as this. But in truth, most people would get to the stage where they'd say Ff is equal to 0.4 times Fn. They'd look at their diagram. They'd say Fn is equal to Fg. They'd say Fg is equal to 20. Therefore, Fn equals 20. You know, they can say, let me show it on here. They can say that that is equal to that by observation. And they know that Fg equals mg, so they can figure it out in their heads. But I wanted to show you this because in principle what you're doing there is you're saying the sum of the forces equals 0. By saying they're balancing, you're saying the sum of the forces equals 0. And if this is on a slope, then your Fg is down there and your Fn is over there, and they're not equal to each other. So there, you've got to be a bit more involved, you know. So I wanted to show you the steps. Okay, let's introduce a skill here. This is, I'd like you to be able to know expressions, you know the equation, and from that equation be able to figure out what a graph would look like. So I say, which trace space represents the relationship between the frictional force and the normal force for an object? So the skill is, you say, well, the frictional force is equal to, it's moving, is equal to mu k times Fn. And I know that that's a constant because it's for an interface. So then I say, oh, I'm plotting Ff versus Fn. So that's like y is equal to, and that's x, well, that's slope, x plus b. What relationship is that in that graph? Is it inverse? Is it linear? Is it parabolic? Is it, what is it? Look at that. There's your y-axis is equal to a constant times your x-axis position. What kind of expression is that? It's going to be linear, isn't it? Yeah? Y is equal to mx plus b. Yeah? Don't like to use m because it means mass. You know, but. So, is it b or is it d? If Fn gets bigger, what happens to Ff? So it's d, isn't it? Now, some people can just look at the expression and go, it's an inverse, or it's an inverse square, or it's, and this is practice. If you can't, then do this. Okay? Your bottom axis is Fn. 1, 2, 3, 4, 5. Let anything you don't know equal 1. There's no law says you can't let it equal 1. What's 1 times 0? 0. What's 1 times 1? 1. What's 1 times 2? 2. What's 1 times 3? 3. What's 1 times 4? 4. What's 1 times 5? 5. There. And you got it. Okay. Later on, I'm going to give you axes where I say that's FF and that's FN, and I'm going to say you plot me the graph, and you got to draw me. I'll give you grid lines on it, and you got to be comfortable going, well, it'll be there, it would be there, it would be there, it would be there, it would be there. And what I find is people are really uncomfortable because I've not given them any numbers. People are not trained to just put their own numbers in and find the relationship. That's the skill I'd eventually like you to get. But I'm going to start you off, when I do these in Physics 1, when I start you off, basically you pick the graph. Sometimes it's inverse, sometimes it's inverse square, sometimes it's parabolic, sometimes it's... And you just look at the equation, you figure it out. So that's a skill that I'd like you to master. A block slides across a level table. The force of friction between the block and the table is 6 newtons. What is the new force of friction if the mass of the block is tripled and the coefficient of the kinetic friction is quadrupled? So there's one setup. And here's another setup. They're not kind of the same. All you know is that the force of friction in this original one was 6 newtons. And you know that the mass of the block was tripled, so if that was 1, this was 3. And you know the coefficient was quadrupled, so if that equaled 1, this equals 4. You know. It's a ratio problem. As engineers, you often don't know the absolute numbers. You just know you double that and you have that and you... This is how you do it. You say, first of all, you've got to know the equation. FF is equal to, we're talking here about block on the table, slides across. FF is equal to mu k times Fn. Okay. FF new over FF old. Always put the new on top because that's the answer you want. FF new over, I knew the old force of friction, it was 6 newtons. Over 6. And that equals mu k new over Fn new over mu k old times Fn old. And that equals... Well, I got to do a little bit more. My Fn is equal to my Fg, and my Fg equals mg. So this is mu k nu, m nu, g nu. I'm not going to play with g. G's the gravitational constant of Earth. I'm not going to mess with that, but I'm going to put it in as if I could. M old, G old. You see where that comes from? So FF nu over 6 is equal to... the coefficient is changed. The new one is 4 times bigger than the old one because it says the coefficient of kinetic friction was quadrupled. If you're not a native speaker, or even if you're a native speaker, and you don't know what quadrupled is, I'll tell you. Stuff like that, I just think especially non-native speakers. It's kind of like quartered, quadrupled, and all that. So that's fair game. You can ask me that. If you ask me what friction is, I'm going to tell you, yeah, you read the book. But, you know. So the simplest ratio is to say the new one is 4 and the old one is 1. You could say 1,000 and 4,000. You could say 27 and 4 times 27. But why not just say 4 and 1? And then the mass is tripled. So that would be, oh, I don't know, maybe 3 and 1. And then G. Well, G's not talked about. It's not changed. It's still on Earth. So if it's not talked about, if you're not told it's changed, the simplest thing is to do is put 1 and 1. You could put 10 and 10 down, or 9.8 and 9.8 down if you want. But it's not changed. I put things that don't change equal to 1. So that gives me 12. I can't tell you how many people will then tell me the answer is 12. And the answer is not 12, because FF new over 6 equals 12. So FF new is equal to 12 times 6, which equals 72 newtons. So this is a so-called ratio problem. I'm sorry?
FFN over 6 equals 4 times 3 times the 1 over 1 ratio. What is that 1 over 1 ratio?
It's G over G, the new G over the old G. And that's why I said you could call it 9.8 over 9.8, or leave it as G over G if you're not changing it. Yeah. They're not hard. You've just never done them before. And it rewards you for writing out the equation. The reason why so many people will tell me it's 12 is because they stopped writing down FFN over 6 a long time ago, because they're all about the math. But they're not, because the math is about equations. The math's not about putting numbers in space somehow. It's kind of like, it's a false economy. It's like, oh, I just put down the numbers that matter. No, the numbers that matter are all of them. You know, if you're doing things in your head or you're doing little jottings at the side, you pay a big price for it. Because you make slips like that where you get 12 and you're forgetting that that's not the answer. The answer is, what is the new force of friction? Not what's the ratio, but you began by working out the ratio. So I think for problems like this, it's a bit like when we did the factor label technique for doing the conversions. We all know how to do them. You just multiply or divide by the conversion factor. But when we do it in our heads, we get them backwards sometimes. And so we lose the points. And it's a bit like this. You know it's ratios. It's just you multiply or divide by the ratios. But which way round is it? So just like the factor label method give you a formalism, so you're not going to make so many mistakes. This also gives you a formalism, so you don't make so many mistakes. So what I'm introducing for this second test is we had concepts and we had word problems in the first one and some diagrams in the first test. Now I'm adding to that and saying, all right, for the second test, I expect you to be able to do some graphical questions. And I'm going to expect you to do some ratio questions. Any equation I could ask you graphically about. I could ask you ratio about. I mean, it's a skill. Think of the course as being content, which is basically the equations. And then the skills that you apply to the content, which is, can you do a word problem? Could you draw me a graph of the relationship? Could you do me a ratio? Can you do a conceptual thing on it? Could you do me a vector diagram when it's a vector? That kind of stuff. So it's two new skills, which I think are really quite valuable. As I say, engineers, you don't always know what the absolute number is, but you know you tripled it. You know you have that, so it kind of keeps things checked for you. Cool. Next time, Let me just show you. I'll just show you. I'll show you one example. Horizontal applied force of 8 Newton causes a 2 kilogram block to slide at a steady speed of 7 meters per second across a level table. What is the coefficient of friction between the block and the table? Mu equals. Try and solve it in one step. What do I know that includes mu? FF is equal to mu k times Fn. So mu k is equal to FF over Fn. Oh, well, that didn't work. Okay. Find FF using. Well, I need to put it on my diagram, don't I? So let's see if I can draw it. FF, the force of friction, must be opposing that 8 Newton force. Oh. Let's resolve forces horizontally. The sum of the forces horizontally is equal to steady speed 0, no acceleration. Oh, plus 8 added to minus Fn is equal to 0. Fn is equal to 8 newtons. Find Fn using, oh, where is Fn? There's Fn. There's also, of course, Fg, which equals mg, which equals 20 newtons. Oh, the sum of the forces vertically equals 0. Plus Fn added to minus 20 is equal to 0. Why have I got Fn suddenly here twice? Because that, I'm sorry, that of course is FF. Duh. And this is Fn. Fn is equal to 20 newtons. Mu k is equal to Ff, which equals 8 over 20. Mu k is equal to 0.4. What are units for mu k? No units. So you're bringing a whole bunch of stuff together. You're resolving forces, you're thinking about friction, you're thinking in two directions, horizontally and vertically. You're thinking one direction at once. I tried to solve it in one step. I found I had two things I had to find out. I found the one thing, then I found the other thing. That's what's coming up next. Same thing on a slope. It means that all your geometry is a little bit harder. You know, it's just, you can't just like eyeball it and go, well, that's the same as that, and that's the same as that. Now it's a little bit more involved. But it's, in principle, no different. Okay? Let's take a break there. And then, so, test. Just prepare. Hopefully you've been doing your homework all the way through and you're prepared